people want to do. Okay. So the question was like why this shouldn't be the magnetic SW6 type stuff, right? So one but one point that we discussed in the observational paper is that although it's a magnetic system in the Quest, there is still no report about detection of the spin period in the outburst, although there are a bunch of like thermals of photometries. And I believe that's the one possible reason that during the outburst, the magnetosphere, because of the increased accretion rate, magnetosphere becomes more and smaller than the white dwarf radius or something. And yeah, that's the one reason we prefer to do it in a disk length model, but it's not excluding, I guess, the magnetic wind model. So magnetic accretion model. So yeah, it's maybe worth checking, is there any sort of like magnetic models that can explain this features as well? It's going to be kind of future work, I believe. But in terms of like observation, that's the one reason. And especially like this kind of, I'm not sure, this kind of narrow but double feature also can coming from the magnetic wind, a magnetic accretion or something. Yeah, I just don't know. Yeah.
Is this guy's orbital period in that quite narrow, range where all the SW6 stars are found? Is it 3 to 4 hours?
Yeah, this is basically a W Sagittarius star. So its orbital period is like 90 minutes or something. So it's at least not in the range for SW6 stars. But yeah, actually what we discussed in the first paper is that it's at least shows lots of similarity with the SW6 stars. So it could be analog, but interpretation of the single peak emission line has like lots of options in the SW6 stars. And we discussed that with winds, it's going to be most explainable for the observational features, but it's not excluding other like magnetic accretion could be another option to explain these features. Yeah. So yes, anyway, I was maybe talking about this evolution. Oh, I finished this one, and sorry, I was talking about this UV spectrum. And actually, the model A was originally designated to reproduce the UV observation. So this is more or less, we say, something that we expect for UV observation. And if we just create the normal spectrum, model 2 is more or less looks like the model A. So although our model 2 is have not, focusing on UV spectrum at all, what we get from the simulation is more or less similar to what we usually expect for the observation in a C4I. So from this optical and UV spectrum, we suspect this kind of disk winds observed in the V45 Andromeda could explain both the optical and UV signature in some novae extras. So here's a bit of summary of this, especially on disk objects. So the first one is why the mass loss rate of this system is very high compared to the other ones, maybe by a factor of 10 or 800. And our understanding is that because this system has a very high accretion rate, let's say 10 to minus 7 solar mass per year, and this is the reason why this system have a high mass, can have a mass loss rate, because in like line-driven winds model or some sort of magnetic winds model, people usually find the proportional ratio between the mass loss rate to the accretion rate. So if the accretion rate goes 10 times higher, we naturally expect the mass loss to go to 10% also order of higher. But at the same time, this mass loss to accretion rate ratio and also wind acceleration radial parameters are very common in the other disk wind models explaining UV and optical features. So we think that this suggests that the wind driving mechanism, if we understood this as a emission line from the disk winds, the wind driving mechanism should be the same as other many wind driving CV system. And as I said, the V45 Andromeda like feature winds also explain spectral evolution. and simultaneously the optical plus UV wind signatures. Oh, by the way, the right bottom panel showing the relation between the accretion rate in the x-axis. Actually, it is presented as an Eddington ratio in this case, and y-axis is for the accretion rate. Mass loss rate of the system from the hydrodynamic simulations. So we usually expect this kind of proportional relation between that, but some accretion rates, the wind stops because there's no more UV observation to derive the wind. And the reason why we missed this kind of very, mass loading, high mass loss rate winds could be due to lack of accurate, like Gaia distance or inclination, especially. It's very hard to determine the inclination for non-eclipsing system in general. So maybe this kind of like in the previous literature back in like 1990s or something may prefer to choose low accretion, low mass loss rate values to explain the observations. Okay, so here is my slide. It's more like about my future possible collaborations, and also if you got interested in, just let me know. So the first one is what we had a question here. So yes, another possible interpretation of this signature or this observed feature is the magnetic accretion, as we discussed. This kind of novae star showing single peak emission line sometimes show the circular polarization, which is people believe coming from the magnetic white dwarf. And as I said, white dwarf, this 345 Andromeda also show white dwarf spin period at least in quiescence. But I guess not that well. So that's the reason I prefer to wind model more. But anyway, it's not rejecting the magnetic accretion model anymore. So it's worth checking or doing some sort of simulation, what is going to be expectation from this kind of magnetic accretion with very high accretion rates. And the other one is it's worth checking, is there any other dwarf samples showing the disk wind signatures? So from my simulation, it is clear that high accretion rate could be a key to drive strong disk wind. So we may look for the very bright system based on Gaia distance. And also from the works in novae stars, the most sensitive line to disk winds is the helium-1 5876 line. And so we may need to go the high resistance spectrum of this kind of line in the dwarf outburst. And classically, like people just focus on like Balmer line, helmet lines. So this kind of, middle wavelengths emission line was just missed in the higher resolution spectrum. So it's maybe worth doing just towarding this specific emission lines. And also dwarf nova is going to be a transient event. So very prompt and intense observation is the key to success. But I believe this is not something we cannot do in the UV lights. This is what we can do in the optical. So especially if we want to do something in the disk wind in the dwarf nova sample, the optical spectrum is going to be a good key to do this kind of stuff. Lastly, there's no astrophysics background, but in the low mass X-ray binaries, people see some sort of wind and jet coupling through the outburst evolution. So it may be worth checking the same things as in dwarf as well, let's say doing the optical plus radial intense follow-up for spectroscopy. And also in X-ray binaries, people see simultaneous UV optical and infrared wind signatures. So this kind of multi-wavelength studies will also benefit for understanding the disk winds and more generally outflow in the dwarf nova and the high-state series. Yeah, and also making some discussion about the similarity and difference between the dwarf nova and almost X-ray binary will help to understand the disk winds, not in dwarf nova or high-state series, but for the accreting system as a whole. Yeah, so that's it from my side. I'm happy to take any question. Thank you very much.
Any questions? Yes.
So just the first question I have is, have you looked for polarization in this object?
You mean during the outburst, right?
B445, and is there any polarization measurements of it?
I'm not at least I think there's no observation during the outburst, but I guess there could be some observation in the quiescence. But I'm not sure. But yeah, but what suggests is basically the magnetic wide draw should be at least everyone I guess agree for its magnetic feature in the quiescence. But I guess there is no polarization observation in the outburst. Yeah.
And a couple of the SW6 stars, they've also had detected certain polarizations. Your last point is very true. The similarity with the wind signatures. I was struck by the plot you had of the H beta line model at 50 degrees and how similar that was to Maxi 1820's disk wind profiles. Last question I have is, you know, the model you have that has an accelerating, radially accelerating wind. What I'm wondering about is that wind rotating? In other words, is the angular momentum in the azimuthal direction conserved?
So yeah, it's basically the let's say the velocity has a velocity basically has two directions. One is just keeping same angular momentum from the accretion disk and plus some let's say project velocity towards the outer one. So they have basically two velocity components, and yeah, the acceleration is basically for the project velocity, not for the. But actually, there's some rotational velocity from the
much smaller.
Yeah, if just goes yeah.
Any more questions? I don't see any question online. Okay, then let's thank Yusuke.
Thank you very much.
Thank you, everyone.
Thank you very much. Thank you, people on Zoom.